Should be. Am I live? Hello? Alright, I am live. Okay, back to the book. Just to make sure it's working. Hello? Yeah, it is working. Awesome. Yeah. Perfect. If I can move this tab group thing to the right. Move to right. Boom. Awesome. So back to practical signal processing book. So, thing I was working on the other day. Last time I was live streaming, I actually figured out. So I took all the samples, divided it by R, which is the maximum, like the peak, the highest, the biggest sample. I mean, the biggest, the max out of all the samples. And then I found the minimum, divided it, max divided by minimum to get the range. And then I took, what is it? Switch the panels. Oh, I'm in the wrong thing again. Then I took, then you take different values. So if you want 8-bit quantization, right, you do, it's 256 or 2 to the power of 8, right? To get 256 for 8-bit quantization. If you want 16-bit, it's 2 to the power of 16. So I just, put this here. So I don't have to keep doing to the power of 2 to the power of whatever. So, yep. So quantization level divided by R, multiply all the sample, everything that's coming in by that. And then I round it back down right here. And then I restore it by doing the opposite. So instead of dividing everything by R, I'm dividing everything by the quantization level or whatever right here. Well, I guess it's not called the quantization level. This is just the quantization amount, I guess. Yeah, just to reverse the process, I do that divided by R. I mean, R divided by that instead. And then I get the output, which I think, if I had to guess what's happening, hang on, do I have like something to write with here? I'm trying to remember what I was using to write with in my other videos. I think it was, what was it? I think it was external. Yeah, I don't think I have it on Windows, but I'll download it. I've been doing everything on Windows just because, like, Reactor, it's easier to run in Windows. Like, you can't run it in Linux. Ableton, it's easier to run in Windows, so you know what? Sometimes some things are just easier in Windows, and you just have to admit that. Audio is not easy to work with in Windows, especially with frickin' jacked or whatever, or jack, or I don't know. Although So many desktops now. If only you could just like move the desktops. Yeah, got a writing application. Sweet, I can draw. If only I had like a tablet. So my guess as to like what that does is, so you know you have like, this is, say your sample is like a sine wave. Boom. Then you have like samples coming in at like a specific rate. This looks terrible, I know. You know, I think there's view. There's more tools, isn't there? Well, toolbar right just makes the application close. That's good. Oh, now it's kind of like opened with everything else. Oh, I see. View, show toolbars, show toolbars. There we go. So let's go back. That's what I was doing. So is there actually change the paper? Grid. There we go. Much better. Now I'm going to draw a line. So say that sample rate's like every 2 or whatever. So let's say is there a sample this is like the sample rate, and it's like you know, collecting samples at like these points in time or whatever. My guess is that quantization thing forces it to be at different times. So like this is like the normal sample rate. Let's say like this is like the quantized one. So boom. Let's say it's also here too. Whatever. Boom, boom. You can put this at every 3. Why not? Yeah, so the quantized one's like, why is shift not working? What the? Oh, I'm gonna do that. Yeah, so the green's the quantized one. So now instead of being at these points, I guess it'd be at here. Let me draw a different color again. And not have the line be like here, 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 and here. So now it's reading back the samples at those points. No, but the sample kind of illustrates it, but I already know that this is kind of wrong. But I think you kind of, so I think, I mean, these blue samples would be like there'd be a lot more of those samples being taken, and this one would kind of like, there would already be blue. Huh, I guess if I had display this a little better. It would be more like, yeah, let me do this. So let's just do on everyone. So these blue vertical lines is the sample rate being taken to the sample, and then reducing the sample rate. So this is the reduced one. It's like half, like every other one. I believe. I have to look at more images in the book. Hmm. Oh, this said. Hang on, now I gotta read the thing again. This is linear quantization. So yeah, this is okay. This is my guess when we change the quantization. So the blue, this dark blue is like the original sample rate. And we're quantizing it to, you know, something else. So the red, this is like where the samples are originally taken. Whoops. Right here. And then I can do in green. This is where the quantized samples are being taken, I think. Because you're reducing the quantization. There's also levels, like, can I do a dotted line? Pretty sure there is a way to do it that I can't think of. Oh, whatever. It's also quantizing it by the amp. Actually, you know what? It might be because there's quantization happening this way. Yeah, I think I'm thinking of it wrong because no, it's quantizing. It's not changing the sample rate. This is, I don't. Yeah, it's not really changing the position. I don't think it's really changing the position of the samples, at least horizontally. I think it's more so changing them vertically. But anyways, I'll just show. So this is
shells at the seashore.
This is with 11-bit quantization.
Shells at the seashore.
This is 10.
I did it. She sells
9.
seashells at the seashore. I did it. She sells
You can
shells at the.
You can tell as we keep going up in quantization, it keeps the quality goes down and it gets super distorted. It's kind of like just like the quantization thing in Ableton. I wonder if I just did that here. Audio effects. What is it? Quantization. Wonder if it'll sound the same. I don't even see the quantizer in here. That's crazy. I know I have it because I just could have swore I just used it. What in the world? Maybe it's called Redux. Is that it? Bit reduction, okay.
She sells seashells at the seashore. I did it. She sells seashells at the seashore. I did it. She sells seashells at the.
That does sound similar, doesn't it? The same type of effect, I'm thinking.
Did it. She sells seashells at the seashore.
This one just sounds quite a bit different though, actually. But okay, so I take all the inputs, divide them by R, which is the range, and then I take out I just only leave the integral part, so I take out all the decimals. So I'm essentially kind of just leaving out the in-between. So that's more like I think that's more like this. Let's make this a different color. So these are like the amplitude levels it's quantized. The sine wave would have to be a lot bigger for this to make sense. So let's make it really freaking big. Yeah. There we go. Then this would be like levels. It's quantized to, it's only linear. If it wasn't linear, then sometimes you might see like, if it was logarithmic, if it was a logarithm, you'd see like bigger gaps up here and smaller gaps down here, so that the quieter samples would sound better. So I think that's why they have logarithmic quantization. So this is the original being sampled at these points. Something like that, right? You know, hang on. Let's just say the vertical lines are the sample rate. So like right here, I think. Yeah. Now it's more like It's not quite perfect, but something like that. Then the quantization is like just moving the gap between them a little further. So it might be like, instead of like this, it might be instead like that. Something like that. Now it's going to quantize to that. I'm just making something up. But yeah, so it's kind of like a spread out version of the original. And it has, it's reducing the quality, as you're doing that. So yeah, that's my best guess of how that works. But once it does that, I mean, yeah, that's once it takes the integral parts, just the integral parts, and it gets rid of the decimal, that's kind of, it almost like spreads it. Wait. Yeah. Kind of like spreads it out a little wider. And then it wanted me to do, and I was working on a different question here too. This. So Mu says this exercise illustrates logarithmic quantitation of audio signals. We will use the same recorded speech vector in the previous exercise. Mu's law quantization converts samples within the range from negative 8191 to positive 8191 into 8-bit values. The sign of the sample is stored in 1 bit of the result, 1 for positive, 0 for negative. From now on, we will only consider the magnitude of the sample. The remaining 7 bits are divided into 3-bit chords. A 3-bit chord, number C, where C is greater than or equal to 0 and less than or equal to 7. 4-bit step at number S, where S is greater than or equal to 0, but it is less than or equal to 15. And then it gives you the formula for the quantization. And it basically says that, so it says, from Mu's law, or Mu law, I guess. Make this 8. 1, 2, 3. Here's a byte. So the first bit is, the sign plus or minus. Then the next 3 bits, well, the first bit is a sign. Then it says three-bit chord, 4-bit step. So this would be the chord values and the byte, and this would be where the step, this is the step. So sine, value, chord values, step. And I just used what? So I took my 8-bit number. So I took the number, I made sure it was in the 8-bit range, less than 128 or greater than equal to negative 128, you know, for a signed 8-bit value. I bit shifted it to the right and then made sure it only included the first bit to get the sign, whether it's positive or negative. You know, if bit right by 7, then I bit shifted it to the right by 4. Then only included the last, you know, only included 3 bits here. So bit shifted it by 4. This made sure to only include 3 bits. Then here, I just only have the, you know, last 4 bits. I and the last 4 bits to get sign, chord, and step. And then the formula for finding the quantization levels based off the sign, chord, and step is, what is it, 2, where S is step and C is chord is, here, I'll just write it down. It's 2S plus 33 times 2 power of C minus 33. So that's how you find a quantization level based on the step and chord values. And you don't even use this sign value, so I don't know why it's there, but it is why you need to get the sign. But so if I have this knob right here, you can see from the negative and positive 8-bit values that it'll show you the sign. Let's see, once it goes in the negative, it'll be 1. If it's in the positive, it's 0. And it'll show you the step and then the quantization level based off that formula that I just wrote down. And my guess, because it said earlier that some values negative 8191 to positive 8191, I think I just have to. So here, I'll read what I gotta do. It says write a program to convert an 8-bit number into a corresponding mu-log quantization level. That's what that does. At least that's what I think it does. I don't know what else it could possibly be doing. Obtain the sign bit from the most significant bit, bit 7, I did that, of the input, the chord number for the most significant bits, 6 down to 4, and the step number from the 4 least significant bits, 3 down to 0. Generate a 256 quantization levels. Now write a program that will take a vector as input of each element and compare it against your entry table and find the nearest one. So, I think we're going to have to scale, because this is just the output here, right? Or from here is just amplitude, from what I understand. I think we're going to have to scale that to the range of negative 8191 to positive 8191. Because this doesn't take floating points. And the weird thing is that it says it takes an 8-bit number, but if I scale this by 8191, that's definitely not an 8-bit number. That's why I question if I should have this here. I should just disregard that completely. And then just do like like this. I think that's how you have to do it. But then once you get the quantization number, you'll have to quantize it. So take these levels and then quantize it to these levels. Take this, quantize it to this, and then you'll have to divide everything by 8191 to put it back into like acceptable ranges. So that's my guess. So let's compare like the quantization level to like this. That's what, 18, this is, huh. So I'm gonna have to take these numbers and find the closest value out of these numbers. The thing is this doesn't go. Quantization levels aren't negative, so I think I'll have to, after I quantize the points, multiply it by the sign value. That's the only thing that makes sense. So, this might take some time. I'd have to go through every sample in here. No, every yeah, because the quantization level is only positive, I'll have to multiply back by the sign. Well, to convert it back, I would have to do I'm just gonna call this mu mode. Mu mode? There, and you just multiply it by that. That's how you get into mu mode. Not Mew. I keep thinking, like, when I hear Mew, I think of like the Pokemon, and I don't know. So that's going into Mew mode. This would be take a sign. It's also going to take what? Quantization level. Just call it QL. No. Whatever. It's going to be called nothing. Now we have to divide by 8191. But then we also have to multiply, I guess. So if it's 0, it's -1. If it's... Hey, wait. Just take the sign value. kid. Wait. Times it by 2 to get the range from... No, I gotta add... Hang on. This will make sense in a second. I'll add 1. So now it's going for... Instead of going from 0 to 1, it's going from 1 to 2. Multiply by 2. Instead of going from 1 to 2, it's going to go to 2 to 4. And then, yeah, then subtract by 2. Now, instead of going from 2 to 4, it's going to go from -1 to +1. Let's see if that's right. In my head, it makes sense, but I might not be processing that right. Wait. Instead of going from 0 to 1, go to 0 to 2. Actually, I could just do it times -1 and then add it to the original signal. No. What am I thinking? Multiply. Yep. So if it's 1, it'll be a negative value. If it's 0, it'll be a positive value. 0. Now it's going to be 1, a positive value. 0, it'll be a negative. Oh. Wait. I'm stupid. You know, I could just do a compare. I don't have to do this. But I just don't want to do a compare for some reason. router. Actually, I think there's like a I greater than. It's greater than z. No, that won't work. It's greater than 0. Whoa. Wait, is there an I latch? Yeah, my bad. -1. This will be +1. Merge them. This will get the sign value. I'll just put a 1 here for now just to test if this works. I don't know why it wouldn't. So if it's 0 is positive, it's 1 is negative. Let's try a different number. All right, it's negative, positive. There we go. Positive, negative. Heck yeah. I'm like confused on what to call this though. This module. I'll put enter mu. I'll just say enter mu and exit mu, I guess. Yeah. That seems right. Now, I have to take the values from here and find the closest value. I gotta read that again. Now write a program that would take your vector as an input for each element and compare it against each entry in your table to find the nearest one. Wait, write a program to convert an 8-bit number into a corresponding mu law quantization level. Obtain the sign bit. Okay. 256. So I think I see what's happening here. What I have to do. What is -128 plus? Oh, that's stupid. What is the range of -28? No, 128, negative 128 to 0 is 128. 128 times 2. Okay. So that's the range for 256 quantization levels. We just have to get it from, so all the levels from negative 128 to here, these are the ones that we have to keep in an array. Got it. We can just use this as an array, and this is our index, right? Why not? Yeah, why not? But now I'm gonna have to, in order to do that, I'd have to scale 0 to 1. Oh, 0 to 256 to this. So we have a numbers coming in from 0 to 256. And we want to convert that to the range of negative 128 to positive. I'll just do an arrow so you don't mistake it with a negative sign. Positive, whoops, 127. Right? Well, what if we just subtract this? What if we just subtract it by 128? So if our input is 0 minus 128, yep. Now let's say we get, okay, that's it. All I have to do is subtract the input by 128. Instead of calling, I'll call this will be the index from 0 to 128. I mean negative, not 0 to 1. Yeah, well, from 0 to 256 is the index. Yeah, that will work. So that's essentially just our array, kind of. All right. Now, problem is we're gonna have to iterate through this a lot. So every time something comes in here, we'll have to iterate through this. Then once we find whatever, if the value that comes out of here is close to this quantization level, then we'll set it equal to this. Yeah. So I need iterator. This is fun. I'm just going to do this so I know it starts at 0. Something like this. Right. Something needs to trigger it. Man, I hope that works. There we go. So now I just do that to get the iteration. I think I'm going to have to do this at the rate of the sample rate clock. Can I? Can't connect to this. I don't know if it'll let me do it that fast, but Yeah. Uh, I'm worried this is like gonna mess everything up.
Seashells at the
Actually, can I do like a system? Yeah, the sample rate clock is too quick. Shouldn't be though.
sea. She sells seashells at the seashore. I did it. Sea. She sells seashells at the seashore. I did it. Sea. She sells seashells at the seashore. I did it. Sea. She sells seashells at the seashore. I did it. Sea. She sells seashells at the seashore. I did it. Sea. She sells seashells at the seashore. I did it. Sea. She sells seashells at the seashore.
Aha! Look at that.
Sea. She sells seashells at the seashore. I did it. Sea. She
All right.
sells seashells.
It's a little strange, but
seashore. I did it. She sells
holy cow.
at the seashore.
That many iterations just blew the frickin' CPU.
Sea.
33%. Oh, that's wonderful. 256 iterations at this every oh, we're gonna have to compare it. Find the closest one. Closest? Close? Close. Is that how you spell closest? Is that right? Closest. CL, I guess so. QL will just stand for quantization level, I guess. Boom. So it'll iterate through all the quantization levels. kind of janky way to do it, I guess, but
Sea, she sells seashells at the seashore. I did it. Sea, she sells seashells at the seashore. I did it. Sea, she sells sea, she sells seashells at.
well, a lower sample rate doesn't use much CPU, I guess. So between these two, once it goes through one iteration, we'll know what the closest is. Maybe I could do something like this. First thing to do is could have make a counter, I get. No. QL mu triggers iteration. Yeah. Trying to make this look kind of neat, I guess. Something like that. Oh boy. So many things. All right, I think I might be done for now and continue this later. I think I'll eventually get it though.